Greetings, my dear listeners. Today we begin a new journey devoted to one of the most beautiful and intriguing ideas in modern astronomy, the concept of the Goldilocks Zone. This is the term scientists use for the region around a star where conditions may be suitable for liquid water, and thus, potentially, for life. Why Goldilocks? The name comes from the Old English fairy tale about a girl who searched for things that were not too hot and not too cold, not too big and not too small, in other words, just right. In the same way, astronomers search for planets that orbit at the right distance from their stars, not so close that water boils away, and not so far that it freezes solid. But the reality is far more complex than simple geometry. Life requires more than water. It needs an atmosphere, chemistry, climate stability, a magnetic field, and the presence of key elements such as carbon and nitrogen. When we speak of the Goldilocks zone, we mean not only orbital distance, but an entire suite of factors that must align for a planet to resemble our own. The history of the idea is fascinating in itself. The term habitable zone entered scientific discourse in the mid-20th century, when researchers first began seriously considering the search for extraterrestrial life. At first, it referred solely to distance from a star, but as astronomy advanced, it became clear that habitability depends on many variables. For instance, Venus and Earth both orbit within the Sun's habitable zone, yet one became a hell of over 400 degrees Celsius, while the other blossomed into a cradle of life. Philosophically, the concept forces us to ask, how unique is Earth? We tend to see it as the natural home of life. But if the Goldilocks zone exists around many stars, then potential homes for life may be far more common than we once thought. This fuels hope that we are not alone. Think of this. Just 20 years ago, we knew of no planets beyond our solar system. Today, thousands of exoplanets have been discovered, and hundreds of them lie within their stars' Goldilocks zones. Some orbit red dwarfs, small, cool stars with lifespans measured in trillions of years. Others orbit yellow suns much like our own. We are only beginning to map the potential neighborhoods of life. The stories of discovery are thrilling. Take the TRAPPIST-1 system revealed in 2017. It boasts 7 planets, with several located in the habitable zone. Scientists dream of the day we can peer into their atmospheres and search for water, oxygen, or even biosignatures. That would be a moment to transform our view of the universe. Yet we must remember, the Goldilocks zone is only the first filter. Being in the right zone does not guarantee life. Venus and Mars remind us of that. Venus succumbed to a runaway greenhouse effect and became a furnace. Mars lost its atmosphere and water. Only Earth maintained balance. Thus, the real search for life demands analysis not only of orbits, but of many other parameters. Philosophically, the Goldilocks zone becomes a metaphor for balance, not only in the cosmos but in our own lives. We too search for what is not too much and not too little, not too fast and not too slow. Life arises where balance is found. Perhaps this is a universal law. Thus, the Goldilocks zone is more than a scientific term. It is an invitation to search. It reminds us that the universe may be full of worlds where conditions are neither too harsh nor too mild, but just right for life. In the chapters ahead, we will explore which stars make the best hosts, which planets stand the greatest chances, and how our technology is bringing us closer to the answer to the great question, where else in the universe might life exist? When we speak of the Goldilocks zone, it is important to realize that not all stars are equally good for life. At first glance, it seems that the more stars, the more potential worlds. But reality is more complicated. Different types of stars create very different environments, and not all are friendly to the emergence and survival of life. Stars vary in mass, temperature, and luminosity. Astronomers classify them by spectral class, from cool red dwarfs of class M to hot blue giants of class O. life as we know it is likely possible only around certain types of stars. Red dwarfs are the most numerous stars in the universe. Their masses are tens of times smaller than the sun's, and they shine faintly. Their great advantage is that they live unimaginably long, trillions of years. This gives an enormous time span for life to arise. Yet they have drawbacks. In their youth, red dwarfs are extremely active, producing powerful flares and radiation that can strip a planet's atmosphere. Moreover, to be in the habitable zone of a red dwarf, a planet must orbit very close. This almost certainly means tidal locking, one side in perpetual daylight, the other in eternal night. Can life survive in such conditions? Scientists debate it. Yellow stars like our sun appear more promising. Their lifetimes are about 10 billion years, long enough for life to arise and evolve. They are stable, not overly active, and provide planets with a relatively wide habitable zone. Earth emerged in such a system, which is why we often consider solar-type stars the best candidates. Blue and white giants, however, are almost entirely excluded. They are too massive and live only a few million years, far too short for life to develop. Even if planets formed there, they would not have time to evolve along Earth's trajectory. Philosophically, this question reminds us that not all conditions are equal. We often imagine the universe as an endless stage of opportunities. But the truth is harsher. Only a few scenarios lead to the harmony we call life. The rest are too fast, too violent, too cold. In this sense, the search for habitable worlds is not a search for chance, but for rare patterns of balance. Astronomy's history is full of changing perspectives. Not long ago, red dwarfs were dismissed as hopeless for life, but with discoveries like TRAPPIST-1 and Proxima Centauri b, scientists are cautiously reconsidering. Perhaps even around such unstable stars, there may be planets with local conditions that sustain life. Think of it. Billions of red dwarfs surround us, each with multiple planets. Even if a small fraction are habitable, that means millions of possible worlds. Could it be that we are being too strict in our judgments? Thus, choosing the star is the first step in the search for life. Red dwarfs offer time but harsh conditions. Yellow stars offer balance, though they are fewer. Blue giants are dazzling but useless for habitability. Each star type is its own story, its own chance. In the chapters ahead, we will discuss how these stellar conditions interact with planets and what factors truly determine whether a world can host life. We have already discussed which stars create favorable conditions for life. Now let us turn to the planets, for it is they that serve as the stage where life may unfold. A key concept here is Earth-like exoplanets, planets similar to our own in size and structure. Why Earth-like planets? The reason is simple. We know only one example of life, and it is bound to Earth. Gas giants like Jupiter and Saturn are unsuitable for life on their own, though their moons may be promising. Still, rocky planets the size of Earth or somewhat larger are considered the prime candidates in the search. What factors make a planet habitable? First is size. A planet must be large enough to retain an atmosphere, but not so massive that its gravity turns the surface into a hell. Earth is a perfect balance. Mars is too small to hold a dense atmosphere, while Venus is slightly larger than Earth and may have tipped into climate catastrophe partly for that reason. Second is the composition of the atmosphere. The atmosphere is both shield and regulator. It traps heat, protects from radiation, and enables the circulation of water. Without it, life as we know it cannot exist. But the atmosphere must be just right. Too much carbon dioxide leads to a greenhouse inferno, too little to a frozen wasteland. Third is the presence of water. We search for life in the form we know, which means we need liquid water. It is the universal solvent, the transport medium for nutrients, the basis for biochemistry. A planet without water remains barren, even if every other factor is perfect. In addition, geological activity is crucial. This may sound surprising, but plate tectonics and volcanism provide long-term climate stability. They recycle carbon between the atmosphere and the interior, preventing both overheating and overcooling. Mars lost this activity, and with it its long-term habitability. Philosophically, the question of planets reminds us that life is always a fragile balance. A little more mass and a world becomes Venus. A little less and it becomes Mars. A slightly different atmosphere and water vanishes. We live on a razor's edge between chaos and harmony, and it is this edge that allowed humanity to appear. The history of exoplanet discoveries shows how we gradually learned to find such worlds. At first, only giants were discovered, easier to detect, but with the development of transit analysis and stellar wobble measurements, planets the size of Earth became visible. Today, dozens of confirmed super-Earths exist, some within their stars' Goldilocks zones. Think of this. If our galaxy has hundreds of billions of stars, and even a small fraction hosts such planets, then the number of potential Earths runs into the billions. Even if only a small portion are habitable, the numbers remain staggering. Thus, the next step after choosing the star is choosing the planet. And Earth-like worlds are the prime candidates in the search for life. In the chapters ahead, we will discuss the roles of moons, the influence of orbits, and the importance of stability for habitability. In the previous chapter, we discussed Earth-like planets as prime candidates for life. But not only planets themselves may be habitable, moons often play a crucial role, and in some cases, they may even be more promising than their parent worlds. Consider our solar system. Jupiter and Saturn are giants unsuitable for life themselves, yet their moons open entire new realms of possibility. Europa, covered with ice, hides beneath its surface an ocean larger than all of Earth's combined. Enceladus shoots geysers of water and organic molecules into space. Titan, with its dense atmosphere and methane lakes, defies our imagination. These examples show that habitability may lie in places we least expect. Philosophically, this reminds us of an important lesson. Life may not appear only in familiar places. We search on planets, but perhaps the most intriguing forms are hidden on moons. This teaches us flexibility, urging us to expand our horizons. Why are moons so promising? First, they receive energy not only from their star, but also from tidal interactions with their planet. This means warmth can persist even far beyond the traditional Goldilocks zone. Second, they may maintain internal geological activity, as with Europa or Enceladus, keeping subsurface oceans liquid. Third, moons can host complex chemical processes, laying the groundwork for biochemistry. The stories of exploration are thrilling. The Galileo spacecraft gave us hints of Europa's ocean. Cassini revealed Enceladus breathing water into space. Huygens descended onto Titan, showing us a world of rain and rivers, of methane. Each discovery broadened our picture of what habitability can mean. Think of this. If our own system hosts several such worlds, how many more might exist in other systems? Each gas giant may have dozens of moons, some with hidden oceans or fascinating chemical cycles. This greatly increases the number of possible homes for life. Philosophically, this broadens the Goldilocks zone itself. It is no longer just a narrow belt around a star, but a vast web of opportunities where energy comes not only from starlight but from gravitational dance. In this sense, the universe is richer than we imagined. Thus, moons represent another critical frontier in the search for life. They remind us that habitability is not a single recipe, but an endless variety of combinations. In the chapters ahead, we will examine how orbits and system stability affect the chances for life to arise and endure. In the previous chapter, we explored moons as possible abodes of life. Now it is time to consider another critical factor: planetary orbits and the stability of their motion. Even if a planet lies in the Goldilocks zone, its path around the star can make life impossible. An orbit determines how much light and heat a planet receives. If it is circular and stable, the climate will be relatively predictable. But if the orbit is highly elongated, eccentric, the planet will sometimes pass too close to the star and sometimes too far away. This creates extreme temperature swings, posing harsh challenges for life. The tilt of a planet's axis also plays a huge role. Earth's tilt of about 23 degrees produces our seasons. If the tilt were much larger, the climate would swing too wildly. If smaller, the planet might have near-perpetual spring, which could also limit ecological diversity. Equally important is the stability of the planetary system itself. In multi-planet systems, massive neighbors can disturb each other's orbits. If a planet in the habitable zone is constantly nudged by a gas giant, its climate may become chaotic. In the worst case, the orbit may destabilize entirely, ejecting the planet from the system. Philosophically, the question of orbits reminds us of the importance of harmony. Life emerges where balance reigns. Not too close, not too far, not too fast, not too slow. Even the slightest disruption may bring chaos. In this sense, an orbit is not just a line in space, but a symbol of stability. The history of discoveries confirms this factor's significance. We know of exoplanets with extreme eccentricities, where temperatures swing by hundreds of degrees. Life there is unlikely. On the other hand, some systems display remarkable stability, with planets circling almost perfect circles for billions of years. Such systems are prime candidates for the search. Consider this. Our own Earth enjoys the perfect combination of orbit, tilt, and neighbors. Had Jupiter been slightly closer, it might have destabilized Earth's orbit. Without the Moon stabilizing our axial tilt, the climate could have been far more erratic. Life, it seems, is the product of rare and delicate coincidences. Thus, orbit is another filter in the search for habitable worlds. Even if a planet lies in the Goldilocks Zone, its motion must be stable enough to sustain life. In the chapters ahead, we will discuss the roles of atmospheres and magnetic fields, and how they can transform potentially suitable worlds into true homes for life. We have already spoken of stars, planets, moons, and orbits, but there is another factor without which life as we know it cannot exist: the atmosphere. The atmosphere is the planet's breath, its skin, and its shield all at once. It shapes climate, regulates temperature, protects from radiation, and allows water to remain liquid. Consider this. Without an atmosphere, Earth would be a frozen desert, where water would either evaporate into space or remain locked in ice. The atmosphere traps heat, creating a greenhouse effect, but within limits. The balance of gases, nitrogen, oxygen, carbon dioxide, and water vapor, made Earth habitable. A little more carbon dioxide, and we would be Venus. A little less, and we would resemble Mars. Atmosphere is not only composition, but also pressure. Water can exist in liquid form only under certain conditions. On Mars, the atmosphere is too thin, so even when ice melts, water evaporates immediately. On Venus, the surface pressure is 90 times that of Earth, turning it into a colossal pressure cooker. The history of exploration shows just how varied atmospheres can be. Titan, a moon of Saturn, has a thick atmosphere where methane rain falls. Gas giants have atmospheres of hydrogen and helium, with storms the size of entire planets. Atmosphere is the key to deciding whether a world can be home to life or remain barren. Philosophically, the atmosphere symbolizes the invisible veil that sustains fragile balance. We breathe it every moment, rarely considering the wonder it represents. Elsewhere it may be toxic, dense, or thin, yet everywhere it ties the heavens and the ground into one. Modern technology now allows us to glimpse the atmospheres of exoplanets. Using telescopes like James Webb, scientists study the light passing through a planet's atmosphere during transit. Spectra reveal the presence of water, methane, carbon dioxide. These are the first steps toward detecting biosignatures, the fingerprints of life. Think of this. If we find a planet whose atmosphere holds both oxygen and methane, it will be almost direct evidence of biology. Such gases cannot coexist for long without constant replenishment. That would be a moment akin to discovering a new continent, but on the scale of the cosmos. Thus, atmosphere is another filter in the search for Goldilocks worlds. It turns a simple rocky planet into a living one, or into a desert. In the chapters ahead, we will discuss the role of magnetic fields in protecting atmospheres, and what happens when that protection is absent. In the previous chapter, we spoke about atmospheres as vital for habitability, but atmospheres cannot endure forever unless protected by another crucial factor, a magnetic field. This invisible shield surrounds a planet, deflecting the deadly flow of charged particles streaming from the star and from deep space. Earth survives thanks to its magnetic field. Generated in its core, where liquid iron moves and spins, it acts like a giant dynamo. The resulting electromagnetic field encircles the planet, deflecting the solar wind. Without it, solar particles would gradually strip away the atmosphere, leaving Earth a barren world like Mars. The history of Mars is a sobering lesson. Once it likely had a dense atmosphere and oceans, but its core cooled, its magnetic field died, and the solar wind began to erode the air. Today, Mars retains only a thin veil of gases, unable to preserve liquid water. It shows us how essential this invisible cloak is. Philosophically, the magnetic field can be seen as a symbol of inner strength. A planet may appear beautiful on the outside, but if it lacks a beating heart to generate protection, it is doomed. Life requires not only external conditions, but inner energy. The lesson extends beyond astronomy into human fate. Magnetic fields are remarkably diverse. Jupiter's is so strong it stretches millions of kilometers, creating radiation belts deadly to spacecraft and life. Mercury's weak field still helps it retain traces of atmosphere. For many exoplanets, magnetic fields remain hypothetical, but new technology will soon allow us to detect them. Current research focuses on how magnetic fields influence habitability. A planet in the Goldilocks zone of a red dwarf will be bombarded by flares and radiation. Without a strong field, its atmosphere would not survive. Thus, scientists increasingly ask, does the planet have an active core and dynamo to generate protection? Consider this. The magnetic field is also responsible for one of Earth's most stunning spectacles, the auroras. These occur when solar particles breach the shield and collide with atmospheric molecules. They are not just beauty, but proof that the shield works, protecting us daily. Thus, the magnetic field is another filter in the search for life. Invisible yet indispensable, without it, a planet is defenseless. In the chapters ahead, we will turn to the chemistry of life, for even if all physical conditions align, without the right building blocks, life may never emerge. In the previous chapter, we spoke of magnetic fields as shields for planets. Now it is time to consider another fundamental aspect, the chemistry of life. Even if a planet lies in the Goldilocks zone, has a stable orbit, an atmosphere, and a magnetic field, without the right chemical elements, life cannot emerge. On Earth, life is built on a handful of key elements: carbon, hydrogen, oxygen, nitrogen, phosphorus, and sulfur. These form DNA, proteins, and lipids, the building blocks of biology. Thus, the question of habitability is inevitably tied to whether a planet possesses enough of these elements. Carbon is the central element of life. Its unique ability to form long chains and complex structures makes it a universal material. We know of no other chemistry that can so effectively sustain diversity. Scientists sometimes speculate about silicon-based life, but for now this remains hypothetical. Hydrogen and oxygen are required for water, the universal solvent. Nitrogen builds amino acids and nucleotides. Phosphorus forms energy molecules such as ATP, while sulfur plays roles in complex biochemical reactions. Together, these create the foundation of life. Earth's history shows how the availability of these elements is linked to geology. Volcanoes, comets, and asteroids delivered organics and water. Catastrophes may have provided the spark for biochemistry. It is a reminder that destruction can seed creation. Philosophically, this frames life as not a miracle beyond matter, but a natural outcome of chemistry. When the right elements meet under suitable conditions, self-organization becomes possible. We are the chemistry of the cosmos made flesh. Modern research searches for chemical traces on other worlds. Enceladus shows organics in its plumes. Mars has yielded phosphorus. Telescopes probe exoplanet atmospheres hunting for methane or oxygen. Each is a step toward finding the building blocks of life elsewhere. Consider this. If the essential elements of life are widespread in the universe, then perhaps life itself is not rare but inevitable. We are but one expression of it. Somewhere among billions of worlds, chemistry is already playing the same game that began on Earth. Thus, the presence of the right elements is another filter in the search for habitable worlds. In the chapters ahead, we will explore how biology and geology interact and why planetary dynamics matter as much as chemistry itself. We have already discussed the role of chemical elements necessary for life. Now let us examine how geology and biology interact to create unique conditions for habitability. A planet is not a static sphere, but a dynamic system where internal processes shape the fate of its inhabitants. On Earth, geological activity has provided long-term climate stability. Plate tectonics regulates the carbon cycle. Volcanoes release it into the atmosphere, while sediments lock it away again. This balance has kept temperatures within habitable limits for billions of years. Imagine a planet without plate tectonics. It may have an atmosphere and water, but without regulation, its climate could spiral out of control. Venus may be an example. Its surface froze under an immobile crust, while greenhouse gases turned it into hell. Too much geology, however, can also be problematic. Constant eruptions and quakes create unstable conditions where life struggles to gain a foothold. Balance, once again, is the key. Philosophically, this reminds us that life is always in dialogue with its planet. We are not separate, but part of a system where crust, air, and ocean move in rhythm. Humanity is as much a child of geology as of biology. Earth's history offers dramatic lessons. The Great Oxidation Event 2.5 billion years ago was driven by microbes releasing oxygen. It reacted with minerals in the crust, altering the atmosphere. Geology and biology together reshaped the planet, enabling complex life. Modern studies show that geological activity may be crucial in the search for extraterrestrial life. Worlds with signs of tectonics, volcanism, or hydrothermal vents are prime candidates. Europa and Enceladus, with ice-covered oceans, likely host geological processes that could provide energy for microbes. Consider this. If biology and geology are inseparable, then the search for life is not just for water or air, but for planets that breathe and change. Life thrives on cycles, not stillness. Thus, planetary dynamics form another filter in the quest for Goldilocks worlds. In the chapters ahead, we will discuss time as a critical factor, how long it takes life to arise, and how long stability must last for it to flourish. We now arrive at a crucial question. How does time affect the possibility of life in the Goldilocks zone? Even if a planet is ideally placed, with an atmosphere, a magnetic field, and rich chemistry, without enough time, life may never emerge. On Earth, the first signs of life appeared about 3.8 billion years ago, soon after the planet cooled and stabilized. But the journey from microbes to complex organisms took billions of years. Had the sun lived only a few 100 million years, like blue giants, this process would have been impossible. Thus, the lifespan of the star and the stability of the system are critical. Philosophically, this raises the question of patience in the cosmos. Life is a slow experiment, taking billions of years. Where time is scarce, the experiment ends. Where time abounds, worlds of diversity may arise. Beyond emergence, time is also needed for survival. Catastrophes like asteroid impacts or supernovae can wipe out life. Yet if a system is stable, life may rebound. Earth endured mass extinctions, but each time the biosphere revived. Stability is not absence of disaster, but resilience through it. Stellar systems illustrate this vividly. Red dwarfs offer immense longevity, trillions of years. Yet their youth is turbulent, bombarding planets with radiation. Yellow stars like the Sun provide a balance, long-lived and moderately active. White and blue giants, by contrast, almost rule life out, burning too fast. Consider this. If life needs billions of years to evolve, which stars are its cradles? Perhaps solar-like stars give the greatest chance. Perhaps under special conditions, even red dwarfs can host life. Scientists are still searching for the answer. Philosophically, time becomes the ultimate filter. It eliminates the fleeting, the unstable, leaving only those that endure. We too are children of time, our bodies and minds shaped in its rhythm. Perhaps this is the sternest law of the universe. Thus, time is a critical factor in the search for Goldilocks worlds. Without it, all else is meaningless. In the chapters ahead, we will explore the technologies that help us seek these worlds, and how humanity is learning to distinguish among thousands of stars those where time, chemistry, and stability meet in harmony. We have spoken of stars, orbits, atmospheres, and time. Now it is time to ask, how does humanity actually search for worlds in the Goldilocks Zone? Not long ago we knew of no exoplanets. Today we can chart entire systems. The first method was radial velocity. As a planet orbits a star, it tugs on it, causing the star to wobble slightly. This wobble is measured by shifts in the star's light spectrum, the Doppler effect. The first exoplanets were discovered this way in the 1990s. Yet this method favors giant planets close to their stars. The next breakthrough was the transit method. If a planet passes in front of its star, the light dims slightly. Modern telescopes can measure this with astonishing precision. The Kepler telescope discovered thousands of exoplanets this way, including many Goldilocks candidates. Today's tools go further. The James Webb Space Telescope can analyze starlight passing through a planet's atmosphere during transit. This lets us study atmospheric composition across vast distances, searching for water or even biosignatures. Another approach is microlensing. When a massive object passes in front of a distant star, its gravity magnifies the starlight like a lens. If the object has planets, they too can be revealed. This method is powerful for planets far from their stars. Philosophically, this is breathtaking. From a small world, we learn to see planets tens or hundreds of light years away. We cannot touch them, yet we study them by the faintest flicker of light. It is like seeing an entire world in the reflection of a shadow. The history of discovery is thrilling. In 1995, the first planet around 51 Pegasi was found, a sensation. Today, thousands more are known. Each one is a story. Some lie in the Goldilocks Zone, making them prime targets for future missions. Consider this. Perhaps we already know the names of planets where life exists, though we have not yet realized it. Their atmospheres await analysis, their spectra interpretation. We stand at the threshold of the greatest discovery in human history. Thus, exoplanet hunting technologies are the key to the Goldilocks Zone. In the chapters ahead, we will explore how future missions and telescopes will bring us closer to the moment when we can finally say, yes, we have found another living world. In the previous chapters, we discussed how humanity detects exoplanets. Now let us look to the future. What missions and technologies will bring us closer to answering the great question, where in the galaxy are the Goldilocks worlds? Today we stand at a unique moment in history. The James Webb Space Telescope has for the first time allowed scientists to analyze the chemical makeup of exoplanet atmospheres. But this is only the beginning. Planned missions promise to make direct observations of potentially habitable planets. One of the most exciting concepts is LUVOIR, a giant space telescope with a mirror over 8 meters across. It will not only search for planets but photograph them directly, suppressing starlight with advanced coronagraphs. Imagine seeing the pale blue disk of a distant world, clouds swirling across it, like a miniature Earth. Another mission is HabEx, a dedicated observatory for habitable planets. Its key innovation is the use of star shades, vast space-borne screens that fly separately from the telescope, blocking starlight so planets can be seen. It is like shading a lamp with your hand to glimpse fireflies nearby. Astrobiology is also advancing, an interdisciplinary science weaving astronomy, chemistry, biology, and geology. New methods model exoplanet conditions and predict which are most promising. Already, computer simulations explore dozens of habitability scenarios. Philosophically, this resembles a new age of discovery. Once, humanity sailed oceans in search of new continents. Today, we sail the cosmos in search of new worlds. The difference is scale. Future generations may look back on our century as the dawn of cosmic geography. The story of technology is inspiring. Just decades ago, it seemed impossible to see a planet around another star. Today, it is routine. In a few more decades, analyzing their oceans or surfaces may be routine as well. Progress is accelerating. Consider this. Within the 21st century, we may capture the first true image of an Earth-like planet. Perhaps we will see hints of green vegetation or seasonal changes in its air. That will be the moment when speculation becomes fact. Thus, the future of Goldilocks searches lies in telescopes, new methods, and cross-disciplinary science. In the chapters ahead, we will explore how these discoveries transform not only astronomy, but humanity's sense of its place in the cosmos. We have spoken of the future of telescopes and technology. But let us now ask a broader question. How do the discoveries of Goldilocks worlds change our understanding of the universe and ourselves? Each discovery is not just a scientific fact, but a challenge to philosophy and culture. Once humanity believed Earth was unique, the sole center of life. Step by step, science dismantled that illusion. First we learned Earth orbits the sun. Then we learned our star is but one among hundreds of billions. Now we know planets are common, circling nearly every star. This reshapes not only astronomy, but our worldview. Philosophically, the question of habitability is tied to the question of loneliness. Are we alone? If life is common, then humanity is but one member of a vast cosmic community, even if we have yet to meet it. If we are unique, then we bear special responsibility for preserving life itself. Ideas of other worlds have long inspired humans. In antiquity, philosophers pondered the plurality of worlds. In the Renaissance, Giordano Bruno died for suggesting stars are suns with planets. Today, what he died for is fact. The question now is not, do other worlds exist, but which may be habitable? Modern discoveries already shift our mindset. When Kepler revealed planets are everywhere, it was a revolution. We now see the galaxy not as empty, but as a garden, full of potential homes. Each Goldilocks candidate deepens this perception. Consider this. If we detect biosignatures, oxygen, methane, or other gases in an alien atmosphere, it will be a turning point for human culture. It will not just be science, but a civilizational shift, like the dawn of the modern era. We will understand life is not an exception, but a rule. Philosophically, this raises the question of meaning. If the universe teems with life, it teems with meanings, waiting to be uncovered. If life is rare, then we must guard it as the greatest treasure. In both cases, Goldilocks worlds push us toward deeper responsibility. Thus, the search for habitable planets is not just science, but self-discovery. In the chapters ahead, we will imagine the future. What happens when we first confirm life beyond Earth, and how that will change humanity's place in the cosmos. We are nearing the end of our journey through Goldilocks worlds. But before drawing conclusions, let us imagine one of the most thrilling scenarios. What happens if we truly discover life on another planet? The question seems simple, yet the consequences are immense. Imagine a telescope detecting oxygen and methane in an exoplanet's atmosphere, gases hard to explain without biology. Such a discovery would change everything: science, philosophy, politics, even religion. First, science would gain proof that life is not unique. Humanity would cease to be an exception and see itself as part of a universal process. This would drive new research, for if life arose at least twice, it may be widespread. Philosophically, this would mark a turning point. For centuries we have asked, are we alone? The answer no would open horizons of meaning. We would no longer see ourselves as central, but as one expression of the universe's creativity. Yet such a discovery would also raise difficult questions. How would religions react? Some would see affirmation of creation's grandeur, others a challenge to dogma. How would politics respond? Perhaps it would inspire cooperation, uniting humanity as one civilization under the stars, but rivalry may also intensify as nations compete to be the first to find life. History shows great discoveries reshape culture. The discovery of the Americas transformed economies and worldviews. Copernicus and Galileo reshaped science itself. Finding life beyond Earth would be even greater. Consider this. The first evidence may come not from a telescope but from a probe exploring a moon like Europa or Enceladus. If microbes are found in their oceans, that would be a second independent biosphere, and that alone would change our picture of the universe. Philosophically, this would end human loneliness. We would understand life is not an accident, but a law. Perhaps it would inspire us to care more for our planet, knowing we are part of a vast web of being. Thus, the discovery of life elsewhere would be a turning point for humanity. In the final chapter, we will ask what place humankind will take in this new picture of the cosmos, and how the search for Goldilocks worlds transforms our understanding of ourselves. We now arrive at the final chapter of our journey through the Goldilocks worlds. We have spoken of stars and planets, moons and orbits, chemistry and time, technology and philosophy. Now the ultimate question remains. What place does humanity hold in this cosmic picture? The discovery of exoplanets has already changed our worldview. We no longer see the solar system as a unique island. We understand the universe is full of worlds. But what does this mean for us? The answer lies at the intersection of science and meaning. Philosophically, the search for Goldilocks worlds is a search for ourselves. When we gaze at distant planets, we are really seeking a mirror for our story. We want to know how rare we are, or how common. We want to know whether life is a rule, not an accident. Consider this. If we find life elsewhere, it will affirm the universality of being. If we remain alone, it will make us guardians of life as the greatest treasure. Either way, the answer will be destiny shaping. It will redefine responsibility, the future, and the meaning of existence. History shows that every great discovery expands our horizons. We found new lands, new sciences, new laws of nature. The search for Goldilocks worlds is the continuation of this path. But now the horizon is the universe itself. Philosophically, we stand at the threshold of a new era. We are the first generation to ask seriously about life in the cosmos and to have the tools to seek it. This gives us a mission. Not only to search, but to be worthy of what we may find. Think of this. Whatever the result, the process itself makes us more human. It teaches patience, humility, curiosity. It reminds us we are part of the universe, not its center. And perhaps this awareness is the most profound discovery of all. Thus our journey ends, but does not conclude. The Goldilocks Zone is not only a cosmic region around stars, it is a symbol of the search for harmony in life. It reflects our desire to find meaning amid the infinite. And perhaps someday, decades or centuries from now, humanity will say, "We have found life beyond Earth." But even now we can say, we search because we believe. And that belief makes us part of the great story of the cosmos.